multi-view rendering. So what is it? Why does it exist? It exists basically to accelerate the use case of rendering to multiple views with the same geometry. So that's kind of a general sort of focus. We've had things that were stepping stones in this direction in previous architectures. This sort of takes it to that full next level of generality. And instead of all the limitations that the previous approaches had, which I'll talk about, it makes it general and a lot more flexible, and so can support a lot more use cases. And fundamentally, it's an acceleration feature to accelerate that use case. And what it does is it accelerates the parts of the pipeline that basically are before you actually need to split into multiple views. So, for example, if you're doing if you share all vertex shading and all the geometry for 2 views, what this feature would accelerate is everything before the rasterization part of the pipeline, right? And we'll talk about some actual examples of that in a second. So here are some sort of potential applications that one would naturally think would work. One is stereo rendering, of course. So this is something that we took a good step towards in the Pascal architecture with single pass stereo, but it's further generalized with this use case. But this is where you have 2 eyes, probably a VR type of use case. They're looking into the same scene, so the geometry is almost all shared. And instead of having to re-render the scene twice, you can just submit the scene once, share whatever computation can be shared between the 2 eyes, at least in terms of on the geometry side. Another potential one, and these are just sort of like, I think sort of common sense, straightforward algorithms that use this feature, is the classic sort of cascaded shadow map example where you have multiple views from the light's perspective that you render shadow maps into, and traditionally you would have to render these using multiple renderings depending on how many cascades that you support. Or there would be other restrictions due to the restrictions in terms of what could be shared between them if you do want to come up with some algorithm that can accelerate this case. With multi-view, you can have 4 completely arbitrary projections and 4 completely arbitrary views for your cascades and render them in one go. Other sort of complex surround use cases, here's sort of an immersive 360 degree or something like that, sort of inside of a cube sort of visualization setup. This requires views that are quite different, obviously, have different projection properties and different view parameters, and so could not really be accelerated before we had the generalizations that we offer now in Turing. Other algorithms, there have been algorithms. There's an old one that we had shown years ago where you sort of jittered the light position when rendering into a shadow map and rendered multiple shadow maps using these different jittered light positions and then combined them to give sort of a soft shadow type of effect. You could accelerate that sort of pseudo area shadow type algorithm. Of course, really the best way to do area shadows is ray tracing, but that's a separate talk, right? But those types of things are possible to accelerate using multi-view rendering. So, like we mentioned, Pascal introduced this idea of single-pass stereo. So how is this different than single-pass stereo? So single-pass stereo in Pascal was really, it wasn't a general feature like we're talking about today. It was very focused on the stereo use case, which is why we called it single-pass stereo. So it only supported 2 views, which is the stereo use case, obviously. And there were really no view-dependent attributes, sort of triangle attributes, vertex attributes, except for the x of the position. That's it. So it was not only sort of stereo rendering, but it had to be stereo where the 2 eyes are in a plane and only vary by the x value between them. And in that case, you could output 2 different x's from, say, your vertex shader, and then accelerate that use case. But it's obviously very limited, right? There's lots of different multiple view sort of setups, which even in the stereo use case, there are different sort of ways to do this, which require more view-dependent attributes than just x, and those were not able to be accelerated by the Pascal single-pass stereo feature. This is sort of a diagram that we had shown with Pascal launch, where instead of like with a traditional setup without any of these features, what you would do, obviously, you'd render the whole left eye, go through your engine, depending on what level you implemented this at, resubmit draw calls and all that stuff for the left eye, re-render everything, do the input assembly and geometry shading and vertex shading and everything separately for the left eye, and then rasterization, of course. And then you do the right eye. So single-pass stereo in Pascal allowed you to, for this limited use case, the reason the planes are sort of warped there for the view planes, because we also had this thing called lens match shading, which had this sort of, for the VR use case, it allowed you to have a projection plane that more matched what a lens's warp sort of characteristics are. But it allowed you to do this in one pass. All right, so the left eye and the right eye could be submitted once, could be, the attributes could be fetched, and triangle setup and triangle vertex shading and all that stuff could be done one time. And then obviously after that in the pipeline, rasterization, pixel shading, any sort of frame buffer operations, those would have to be done for each eye, but everything before that would be accelerated. So with multi-view, the generalization here is that we can support 4 views now. And the biggest thing really is this real view-dependent attributes feature, right? So instead of just having position X be view-dependent, now we can have all the position values, X, Y, Z, W be view-dependent, and also any of the sort of attributes that you would normally output from a geometry stage of the pipeline can be view-dependent. So we'll talk about how you actually make those view-dependent in a minute. And it's also important to note that from the pixel shader's point of view, this all happens before the pixel shader gets run. So by the time the pixel shader is executed, it has its appropriate attributes that are appropriate to it, depending on what view it's in. If you're interested, you can know what view you're in. There's a system value that allows you that you can query, which gives you the view ID. So typically, I'll show some pseudocode in a second, but typically the way you would code up like your vertex shader or something is that you would reference this system value, which would pull some constant buffer parameters or something for your matrices that are appropriate for this view, and then do your transformation with the view appropriate data. That's the point at which you would generate view-dependent work. So it's important to note that multi-view is a strict superset of single-pass stereo. Everything that single-pass stereo could do and all the performance that you would expect with single-pass stereo you can get with this new feature as well. You just get a lot more generality. So it can look sort of like this. This is sort of a mock-up diagram here of different use cases. There have been some headsets that are coming soon and some that have been announced that have sort of very wide FOVs. And so if you have an extremely wide, say over 200-degree FOV in the horizontal direction that you want to be able to support, doing it with 2 projections is sort of nasty. You'll get like bad shearing and warping in the edges. So ideally, you would be able to do it with more than 2, say 4 projections. And also, this would allow you to say vary the resolution in the periphery to better match the user's visual acuity, stuff like that. That obviously wouldn't be possible with single-pass stereo. Also, there are headsets now that have canted displays where the 2 eyes are not actually sitting in a single plane. That also could not be supported properly with the old Pascal-style single-pass stereo, right? So even for the sort of VR-ish use case, the Pascal single-pass stereo was starting to be limited, and it was not necessarily going to scale to next generation of displays, whereas the Turing multi-view feature allows you to support much more flexible and interesting sort of VR use cases. So talking a little bit about the actual implementation. So like I said, you have reference to this view ID. In DX12, there's this SV view ID system value that you can reference inside your shaders, which tells you which view, which allows you to do things that are a function of view ID. We have support for this in all the major APIs right now, I think, or it's coming. I think it's available right now, or will be shortly. And one performance gotcha that we actually ran into this. I mean, this stuff is all like super hot, right? We're working on this stuff just in the last few months, right? And we're learning how best to use these features as well, right? In terms of, typically a lot of the sort of performance things and stuff in terms of real world use cases and stuff, is something that takes a little bit of time to learn. One thing we recently noticed is something to be careful of because it's natural, because of the generality of this feature, it's easy to write code that is sort of very general and looks nice, which is how you should write code, but then you may not get the same performance as, say, the old single-pass stereo feature for cases which could have been accelerated by that old feature as well. And one of the things we notice is this last point here where it's important to note that there is a cost associated with any attributes out of your shaders, your vertex shaders, that are a function of UID. So I'll show a little pseudocode here to show what I mean. For example, in something like this, where you're doing this math as a function of UID. Here, you're computing some view space positions for your light eye and your current vertex. And then you're doing some math to pass out some output attributes. This is just pseudocode. They're a function of those things that you computed there. So there's a cost associated with this, right? Had those attributes not been functions, like if you just go back through the dependency chain, this is obviously a very trivial dependency chain I show here, but if we had a complex dependency chain, it might be more hard to notice this. But if view ID is referenced in that dependency chain, then that attribute will be more expensive than if it had not been referenced. And so it's just something to keep in mind. You know, like in this example or in other examples like this, oftentimes it could just be a matter of reformulating the math that you're doing to not be doing things in view space and instead be doing things in world space or something like that. I think probably whatever this sort of somewhat silly pseudocode would have been doing probably could have been reformulated to not be a function of the view, and then it would be faster, potentially. Obviously, that all depends on you being actually limited by attributes or even vertex processing at all. That being said, this feature is most useful when you are actually limited in that way. And so this case could actually end up hitting you, right? So there's lots of things. Like I said, the smartest way would be probably to just reformulate it to be not a function of the view by doing things in world space or just changing the coordinate space in which you operate. If that's not possible, you could even, if you're totally not pixel shader bound or fragment processing bound, you could actually just consider computing some of these view-dependent attributes in the pixel shader instead of passing them down as view-dependent attributes. And that obviously increases the pixel shader cost, but if that's not the bottleneck, that's not a problem, and it lightens the cost in terms of attributes. So just something to keep in mind.